SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering, Module 2, Vapor Power System Part 3. In this lecture, our main intention is to study feed water heaters. So, here the learning components would be as follows. First one is the condenser and feed water systems, which we discussed in our last class. Then we will revisit the regenerative cycles, which was studied in the beginning of this module. Why we go for this regenerative cycle? Because this regenerative cycle uses closed and open feed water concepts. So, we will try to see thermodynamic viewpoints, some of the design aspects of closed and open type of feed water heaters. Then towards the last segment, we will discuss something about boiler treatment concepts. So, let us start with this concept of condenser and feed water systems. We discussed this concept in our previous lectures, where in a condensate feed water systems, the condenser plays a dominant role, and during this condensation process, the steam from the turbine exit loses heats and condense to liquid water. So, this is the part of or role of condenser, but at the same time the story does not stop here. Rather, we also require feed water systems that can supply the required quantity of water and at a pressure which is desired at the boiler end. So, that is the reasons, and in fact, in either you look at condenser or feed water systems directly, which is supplied from the atmospheric reservoirs. So, all these things comes under the single entity, and we call this as a feed water systems. And moreover, the feed water is normally supplied at an elevated temperature to reduce the boiler load. That is the another kind of requirement that we need for this power plant system. All these needs has to be addressed by these thermodynamic concepts which we discussed earlier, that is through regenerative cycles. So, let us see how this regenerative cycle concept helps us in deciding the role of the feed water heater systems. To give the brief concepts, that combined analysis of condenser and feed water heaters is called condensate feed water systems, and the plant heat rejection systems also deals with circulating water treated separately through cooling water, and that cooling water through cooling towers. That water supplied from the cooling tower is also part of this feed water system. But the role of condenser is only to condense the exhaust steam from the turbines, and it should recover high quality feed water to be reused in the cycles. So, considering all these things, let us see how this modified Rankine cycle can help us. So, in our earlier discussions in modified Rankine cycle, it was emphasized that the necessity of the regenerative feed water heaters is required for improving the cycle performance, and the role of these feed water heaters is to raise the temperatures of the water before it enters to the steam drum or steam generator, and by doing so they raise the temperature up to 200 to 250 degrees centigrades. So, that is the reason and when you rise this temperature to this end, then obviously the boiler load also will come down. So, essentially these feed water heaters are a kind of a heat exchangers, either a closed type or open type. Closed type means the streams are not allowed to mix while exchanging the heat, but in a open type or direct contact type or deaerating type heaters, the streams are allowed to mix, and when they mix, obviously they will come back to a single temperature and pressure. So, that is maybe you can say drawback for a open type or direct contact type feed water heaters. Now, let us revisit the modified Rankine cycle, and one of the concept was a regenerative cycle. So, the concept of regenerative cycle is that if you look at this thermal circuit of a simple or of a modified Rankine cycle, we have a steam generator and there are two stages of turbines, we have condenser, pump, and additionally we have a unit called what is called as closed feed water heater. What is this means is that essentially what we require is that at the exit of the condenser, the thermodynamic state of this is at saturated liquid state, that is state 4, and this has to be pumped to the generator pressure, that liquid has to be pumped. But essentially when you want to pump it, we also need that temperature of this water has to be increased just to reduce the boiler load. And to achieve this, what normally is done is you tap some of the steams from the one of the turbine end, that is one is high pressure or the other is low pressure turbine. So, you tap some of the steam from the HP turbine and then that heat we use it to heat the water. So, essentially we do this dual load, and through this heating process the steam will get condensed and again they will be trapped again in the liquid mode to again goes back to condenser. So, this is the concept of tapping the water or steam from some of the end of turbine and reusing its heat for heating the water. And when you say this particular thermal circuit is for a regenerative feed water systems which involves closed feed water heater. The by closed feed water heater means it is a kind of a cell and tube heat exchanger where the temperature of the steam is dropped, that is because it exchanges heat to the water that is at the outlet of the pump, and this water, heated water, is again goes to the steam generated at its desired pressures. And here main intention is that both the streams, that is steam that is tapped from this turbine and the water that enters from the pump, they do not mix. So, that is the thing you call this as a closed type feed water systems. So, here the concept goes which you have already discussed so far, like if you say 1 unit of steam that enters into the first stage of turbine, that is HP turbine, and at state 2 we take y unit of steam and rest 1 minus y unit of the steam expands in the turbine and then they condenses in the condenser. So, liquid water enters into the pump, then this y unit of steam heats the 1 minus y unit of water, so that we get back 1 unit of steam at the state 6. So, through this process we can do the mass balance and energy balance for the closed water feed water systems. Now, for the closed type feed water systems, we can write the mass balance equations, that is M1 which is entering from the state 1 is diverted by 2 parts, one goes M3 dot, other goes M2 dot. So, that M2 plus M3 becomes M1. Now, if you take the ratio M3 dot by M1 as 1 minus y and y is equal to M2 dot by M1 dash, then that means this one becomes 1 unit and you take y unit this side and here it becomes 1 minus y unit. So, thereby we write these equations, that is ratio of M3 by M1 and as equal to 1 minus y, and y is equal to m2 dash by m1 dash. Now, for this single unit of steam, we can write the energy rate balance, that is y times H2 minus H7 plus H5 minus H6 is equal to 0. This energy balance is done at the open type, that is feed water. So, for feed water we write this energy balance by these equations. So, thereby we can get back what is the actually the fraction of the steam which is extracted. Then obviously we can get back the turbine work, that is in the first stage of turbine we get H1 minus H2, and in the second stage turbine we get H2 minus H3, but the steam flow rate is 1 minus y. And similarly for pump work we have H5 minus H4, that is one single pump which is here. And obviously we will see that when you see the heat added for the working fluid, it will be, since already it is at elevated temperature. So, essentially the temperature has already gone to state 6. So, actually it is H1 minus H6, somewhere 0.6 it will be, heat will be added, and this temperature from H5 to H6 is attained by the feed water system. So, heat energy rejected by the cooling water, which is Q out, it is H3 minus H4 into y times H3 minus H8. So, these things was discussed in the regenerative cycle. There is another concept in the same regenerative cycle study, that is open feed water concepts. So, in our last analysis, when you say closed water systems, the two streams, that is tapped steam from the turbine and the water from the pump, they are not allowed to mix. But in open feed water systems, it is a direct contact type heat exchanger in which streams at different temperatures mix to form an intermediate temperatures. So, this mixing is done in this open feed water unit, and obviously when there is a mixing, and this you can see that the y unit of steam which is at state 2 and is at a different pressure, and 1 minus y unit of liquid water from the at the exit of the pump is also at different pressure and temperatures. When they are mixing, the combined systems has a thermodynamic state at 6, where the pressure and temperatures are not same at which they enter. So, we require another pump, because that pumping system has to be done, because we require the water to be pumped, although its temperature has increased, but the pressure again drops. So, we require a second pump which can push this water to boiler pressure or steam generator pressure. So, that is the reason we require two pumps in a open feed water regenerative cycles. So, rest of the concept remains same, and if you do this analysis for an open type feed water system for a regenerative cycle, similar study we can make, that is mass balance and energy balance equations for open type of feed water. Only difference is that if you look at this circuit, we can say, when you say for open feed water, the y units of steam at enthalpy state 2 enters, and again another entry comes from H5 state, that is from prompt end, and that is 1 minus y unit into at state 5, but what is leaving is minus H6, that is y plus 1 minus y becomes only 1 unit, that is H6. So, from this we can get back what is the fraction of steam which is extracted from at state 2. And in this analysis also we can calculate the what is the turbine work, it is H1 minus H2 plus 1 minus y times H2 minus H3. Similarly, there are two pumps, one at WP1 and WP2. So, for pump, that means for this pump, that is first pump 1, we have 1 minus y unit of steam water, and it is into H5 minus H4, its enthalpy, and for second pump it goes from H6 to H7, that is only for 1 unit of fluid, working fluid. So, thereby we can also find out here, that is if you look at this particular diagram, picture becomes clear So, in open feed water, that is, you take one unit here, goes y unit, 1 minus y unit further expands, this y unit goes to state 6 and then it is pumped to state 7 and again 1 minus y unit goes in the condenser line. So, it goes to, in the first pump it goes to state 5, then it mixes with state 6 and finally 1 unit goes to, so it is again becomes 1 unit goes to 7. So, thereby pressure as well as temperature is increased in a regenerative cycle with open feed water heater arrangement. So, this is all about the thermodynamic aspects. Now, let us go still further, that what essentially we need to know for a closed and open feed waters. In terms of, what are the typical arrangements normally we do? We all know that these closed feed water heaters, they are nothing but heat exchangers, and they are also a similar kind of cell and tube type heat exchangers. So, cell is considered for steam which is tapped from the turbine, and tube is considered for the water that enters from the pump end, and between and within this feed water heater there is a exchange of heat. Now, through this exchange process, what happens? If you look at this particular diagram, ideally it is, if you say steam that comes from the here state 2 is a kind of a superheated region and its temperature, so it drops first. So, when the temperature drops first, so that means we say it is a de-superheating zone. So, in the first process its temperature drops. Now, when it reaches to this saturated point, that is when it is at saturated vapor at state 2, then steam starts condensing, that means in this closed feed water system. So, when it condenses, it releases latent heat of vaporization and then it reaches to saturated liquid. So, saturated liquid means which is tapped from this at state 7. And then there is a subcooling zone, and this is second part we call this as a condensing zone, and third is subcooling zone. So, during the subcooling the further drop in temperature takes place from 3 to 4. So, basically speaking, the steam follows a reverse path what is normally done in a reheater or boiler unit, and that is through this process the feed water temperatures sequentially increased from 5, 6, 7 and 8. So, this concept is similar to condenser, but its role is completely different as that of condenser. Here role of the feed water system is to supply necessary heat for the steam, for the water to reach the boiler pressure. Then there are some words that we are used, that is cell side stream is called blade stream, and typically for large steam power systems we have a low suppose you trap the steam from the low pressure turbine that is at 40 bar, and if you trap it for 80 bar, that is from the high pressure turbine, it is maybe goes to around 80 bar. So, in other words we can say that feed water systems should have capability to operate at this high pressure range. So, that is the reason normally closed type of feed water system is preferred, because they can handle such a large pressure drops. Then this heater has some units we call as a de-superheating zone, where the steam is cooled to saturation temperature. It is followed by a condensing zone where latent heat of evaporation is removed, and then finally steam is condensed to saturation temperatures. Then there are some word that is used, what we are used is that heater drain. So, the condensing zone which is somewhere here between 2 to 3 for the steam, that point of time the steam releases the latent heat of vaporizations. So, this liquid which is formed is called as heater drain for all types of feed water heaters. Similarly, there is a subcooling zone where drain cooling zone in which steam is cooled below the saturation temperatures. So, in general the closed type of feed water systems can have 3 zone type, 2 zone type or a single zone type depending on the nature of heat release. So, depending on the condition of steam at state 2, one can imagine or one can design the feed water either with having a 3 zone type or 2 zone type, or in fact can be a single zone type. So, depending on the needs. For example, for suppling zone we may have different arrangement, that means we can design the feed water only for condensing zone, and in most of the cases it is preferred to use this condensing zone type feed water unit. And the orientation and location should be at par, either it can be vertical or horizontal positions depending on the availability of the pressure line. That is, if it is high pressure line, whether you can the feed water has to be operated in connection with high pressure turbine or low pressure turbine, that depends on the location and space availability for the power plant system unit. Now, let us see what are the some of the heat transfer concepts. So, we all know that while designing these feed waters, we also need to calculate what is the heat load. A general expression of heat load can be represented as Q is equal to U times area, outer area into delta Tm, and this delta Tm stands as a logarithmic mean temperature difference. And by definitions, for depending, let us say if you are looking at a condensing zone unit, and this LMTD is defined by this expression taking the temperature into considerations as delta Ti here and delta Te here in this end. So, if it is only operating in the condensing zone, LMTD expressions becomes follows this expression. This is one aspect. Second aspect is that how to consider the overall heat transfer coefficients. This overall heat transfer coefficient takes care about the convective heat transfer coefficients at the outer surface, convective heat transfer coefficient at the inner surface, and then considering the thermal conduction within the thickness of the tube. So, overall heat transfer coefficients can be calculated, and many times what happens to area, that area it can be outer area, or many times we can assume the mean area or logarithmic area, or you can can write closely as average area of outer and inner surface. So, that way approximations can be made for area. So, through this way we can go for area calculations, LMTD calculations and U calculations, overall heat transfer calculations separately, and that can be used by these equations to find the heat load. And of course, there are drop in pressure for the feed water systems. So, because obviously there will be pressure drops, however, there is no standard calculations for this pressure drop, rather some of the experimental evidence talks about some empirical relations where the pressure drop is measured in terms of PSI, which involves approximate temperature, average temperature at in the Fahrenheit degree centigrade, inside tube diameter in inch. So, and number of passes and length, depending on this we can get these expressions. Okay, this just to give some glimpses that how pressure drops in a closed feed water systems can be calculated. Then moving further, the another concept which drops in is this open type of feed water, and here main constants what we have discussed so far is that open feed water systems allows both the steam and water to be mixed together, but then problem arises that the steam may be high quality steam, but the water may have lot of impurities. So, when they mix together, there are formations of gas formations, there may be possibility of oxygen concentrations, there could be possibility of non condensable gases. So, these possibility, because this is a very common problem when we mix multiple streams together in a direct contact type or deaerating heaters, and again there are possibility of air leakage into these systems, and these are not actually, it is not possible to avoid these non condensable gases. So, that is the reasons we must limit these oxygen concentrations to some value, because they gives many unwanted behavior such as corrosion in these tubes, the overall heat transfer coefficient gets reduced. So, considering this, there is a limit to keep oxygen concentration in the range of 0.005 centimeter cube per liter. Of course, the possibility of open feed water type may be spray type, tray type or combination of spray and tray type, which we are not going deep into details. The next part of our discussion is on this is all about feed water systems. Now, let us think about something some concepts about the boiler treatment. What does this mean by boiler treatment? Many times what happens over the period of time in a steam power unit, when the boiler or steam generator operates continuously, there are chances that we require some kind of overhauling, means removing corroded surfaces, replacing many components. So, that reason we require some kind of boiler treatment or overhauling. And since it is a continuous operation, steam power system is a continuous 24/7 throughout the year operation. So, it is normally very difficult to completely shut down the systems. So, while operating them, we must treat the water quality. So, that is the concept we call as a boiler treatment. So, what are the possibilities that because since we are dealing with water and when there is a presence of oxygen in the steam or water system, then there is a possibility of corrosions. So, for that thing, to avoid corrosions, we require some kind of chemical treatment. So, that is what we call as a boiler treatment. This is one aspect. Second aspect is when the boiler runs continuously or power plant run continuously, we also require, there is a standard loss of 1.5 to 2% loss of water. That means, the requirement of water, there is in cycle by cycle when it operates, there is a every time there is a loss about 2%. So, that makeup water has to come from some other sources. So, we call this as a boiler makeup. So, entire things we call this as a boiler treatment. So, this boiler treatment involves the water makeup system. The water makeup systems we require a pre-treatment, which means removal of chlorine from the contents of raw water. Other is demineralization, which means process that removes dissolved salts through by ion exchange. Second part is we also require high quality of steam. That means, in the thermal circuit we must reduce the non-condensable gases. So, at the end the boiler makeup produces high quality makeup water, but still there are impurities in the journeying of water for various components. And for example, this is one part at the boiler end and again at the condensate polishing. Then we also use some kind of condensate polishings where the condensate is allowed to pass through demineralization vessels, which contains both cation and anion resins. They capture all kind of dissolved solids and act as a filter and for the impurities and suspended solids. So, this is one way that we say boiler blow down lines are periodically removed. That means, there are boiler blow down lines that periodically remove the portion of water from the steam drum and where the concentration is high due to steam flashing, and this blow down is then further cooled and treated for reuse. So, this some of the steams are trapped additionally for this blow down process during the boiler blow down process. Another kind of treatment normally we use by using the word evaporators. So, evaporator is another kind of concepts that we normally use as a boiler makeup that uses flash type distill units, and there are possibility of using single effect and multi effect evaporators. What normally is done in this evaporator is that for the makeup water what we do is we keep this pre-treated water for at state W in a cell. So, this is what we call as a cell, and this water is almost means half of this cell is completely filled with the pre-treated water. Now, inside this we put this evaporators, and in the evaporators what normally the entry line for the evaporator is the motive steam. Motive steam is nothing but with the steam which is trapped from these various ends of the turbines. So, they are basically high quality steams, and when we say motive steams, and basically pre-treated water gets treated through these motive streams, and only high quality vapors at V goes to the power plant or goes to the plant again. So, essentially some of the steam gets trapped from the turbine, which is a very high quality, and these high quality steams takes all kind of impurities from the pre-treated water, and it supplies only vapor to the plant, and thereby the condensate leaves to the plant for again further treatment. So, this is what we call as a single effect type evaporator. Now, another concept that extends for the double effect type of evaporator means is that in a double evaporator type plant systems, the exit from this single evaporator unit goes to the second stage evaporating unit, another stage. So, another stage also does the same thing, and finally, the plant receives, instead of V, it will receive that V2. That means, actual vapor, this is called vapor to the plant. So, idea of using this is that to get quality water or quality vapor for the plant systems. And why do you do this? Because we need to pre-treat this raw water. How do you retreat this water? We buy through this motive steam which is tapped from the turbine end. So, in a single evaporator system unit, preheated raw water is introduced at point W, steam from the plant known as motive steam is introduced at point M, that goes through the steam chest and subsequently discharged as a condensate at point C at relatively low pressure. The preheated water boils and pure saturated vapor is extracted as a makeup water to the plant at point V. And this as I mentioned, we need to have that entire unit, that evaporator unit should be submerged in this water which is contained in this cell. We also define the heat head, which is the difference between the saturation temperature of motive stream, this is heat head, but heat load is the heat load between these things, that by virtue of this heat head the heat load is defined. So, heat head is nothing but the difference between the saturation temperature of the motive stream, which is this, and the raw water temperatures, and corresponding to this temperature difference we can calculate the heat load. And the heat heads, there are considerations that heat heads below freezing temperature is not effective, above 35 degree centigrade is also not effective. So, effective zone of heat heads is 2 degree to 14 degree centigrades. And there is also a concept because since we are dealing with tubes and we require the determination of overall heat transfer coefficient for the evaporator, and which is essentially the function of the motive stream saturation temperature and heat loads. One more important point I need to emphasize is that for 1 unit of motive stream, the single effect evaporators produce 0.8 units of vapors, while double effect and triple effect evaporators produce 1.5 to and 2 units of vapors. But when you go for the double effect evaporators, they add complexity and capital cost. So, although we get the vapor quantity almost 2 times in a triple effect evaporator, but the capital cost and complexity of the system gets increased. So, this is all about the condenser and feed water systems, and we will try to solve one particular problems which was done for a regenerative cycle concepts. Of course, just to see the importance of an feed water systems in a thermal power systems. Okay, let us consider a regenerative cycles. For these problems, I urge the learners to revisit the modified Rankine cycles based for regenerative, that includes regenerative cycles. So, to understand these regenerative cycles things, and we also expect the learners to be familiar with the use of steam tables and to solve these problems. So, let us try to understand. I have explained this thermal circuit of regenerative cycle many times, and I will try to link this particular problem with this thermal circuit. So, the problem statement goes like this. Here the most emphasis is not for the regenerative cycle, here the main emphasis is to do the thermodynamic analysis for the open feed water systems. Okay. So, to give this more emphasis, let us see these regenerative cycles, and what the problem statement says that steam enters the turbine at 8 MPa and 480 degree centigrades. So, the state 1 I can say it is 8 MPa megapascal and 480 degree centigrade, and it expands to a pressure of 0.7 megapascals. So, at point 2 somewhere here it is pressure is 0.7 megapascal, and in this situation the sum of the steam is extracted, that is Y unit, by this feed water heater unit. The saturated liquid leaves the heater at 0.7 megapascal, that means here we say saturated liquid, that is at state 6, and that pressure is 0.7 megapascal. If you see in this particular thermal circuit line, they are at same pressure. The remaining steam further expands in this second stage turbines. So, we have taken Y, so 1 minus Y unit enters into the next turbines. Here it will be low pressure turbine, first one would be high pressure turbine. So, 1 minus Y units again expands in the second stage turbine, and they further expands in the condenser. So, after condensing, that is at state 3, it enters into the condenser and goes at state 4, and from the 4 to 5 there is a first stage pump, and then 5 to 6 is a open feed water systems, and in the 6 both 1 minus Y and Y unit of merge, they gives 1 unit again here. And also we have mentioned the isentropic efficiencies. So, thereby what we may have is that we may revise this diagram something like this, that is here it will be 2s, it will be 2, here it will be 3s, and that will be 3. So, we say 1 unit, Y unit, 1 minus Y unit. So, all these data are given. So, the first step 1 is calculate all enthalpies at state points. To calculate all the enthalpies for the state point, we require steam table. Now, for this steam table, what data we know already, that is state 1, P1 as 8 megapascal, T1 480 degree centigrade, state 2 and as well as 6, we have P2 as 0.7 megapascal, state 3 and 4, we have P3 0.008 megapascal, and some of them are saturated liquid state and some will be in the saturated vapor state. So, accordingly we have this turbine efficiency as 85% and pump efficiencies they are also 85%. So, this data is also given. Pump efficiency means here you can have another line like this. So, considering this data and from our previous discussions, one can find out from the stream table various values, but coordinates of this enthalpies. So, our data table gives us that I am just writing down the end values which is extracted from the streams table, and whatever enthalpies we require, only those numbers I am writing. So, enthalpies at state 1 is 3348.4 kilojoule per kg, H2 is equal to 2832.8 kilojoule per kg. Then H3 that can be calculated from the turbine efficiency, that is 2249.3 kilojoule per kg. H4 is nothing but HF at 0.008 megapascal. So, this value is H4 is 173.88 kilojoule per kg. Then H5 is H4 plus V4 into P5 minus P4. So, this number is 174.6 kilojoule per kg. Then H6 is nothing but HF at 0.7 megapascal. So, this value is 697.22 kilojoule per kg. Then what is H7 is equal to H6 plus V6 into P7 minus P6. So, this number is 705.3 kilojoule per kg. So, through this process we know all these enthalpies at the all state points. Then let us try to find out the analysis for open feed water. For open feed water, we write these expressions y, that is for this unit we can say y times H2 plus 1 minus y times H5 is equal to H6. So, from these equations we can find out what is y, which is H6 minus H5 by H2 minus H5. So, by inserting the number we say 697.22 minus 174.6 divided by 2832.28 minus 174.6. So, y value becomes 0.1966. Okay. So, once you know y, then rest of the problems are very simple. First is working calculations for thermal efficiency. So, thermal efficiency is nothing but turbine work minus pump work per unit mass flow rate stream, that is m1 dot, which is at state 1, divided by heat addition q dot in by m1 dot. Okay. So, what is this w dot t by m1 dot becomes H7 minus H6 plus 1 minus y times H5 minus H4. All these enthalpy values are noted. So, this value is Wt by m1 dot becomes this is expression is for pump. So, this is pump expressions, W dot P by m1 dot it becomes 8.7 kilojoule per kg, and for turbine value work output per unit mass flow rate of steam for turbine is H1 minus H2 plus 1 minus Y times H2 minus H3. So, this becomes W dot T by M1 dot is 984.4 kilojoule per kg. Now, heat addition Q dot in by M1 dot becomes H1 minus H7. So, this value is 2643.1 kilojoule per kg. So, noting all these numbers, we write thermal efficiency for the plant is 984.7 minus 8.7 divided by 2643.1. So, this number is 0.37 or approximately 37%. That means, through this regenerative cycle with open feed water systems, we can see that thermal efficiency from this will be higher as compared to conventional cycle. So, this is the efficiency range for a regenerative type cycle. Second part of these things, we need to calculate mass flow rate. So, mass flow rate means we require the output power, that means W dot cycle becomes W dot pump minus W dot turbine is 90 megawatt. This value was calculated per unit mass flow rate. So, this means mass flow rate M1 dot would be 90 into 3600 into, because you need to convert into kg per hour. So, this will be multiplied by 1000 divided by, because these numbers are in kilojoules. So, we need to bring down this 90 into megajoule into kilojoules, and this will be 984.4 minus 8.7, that is the net work. Okay. So, from this M1 dot, that is mass flow rate of steam entering to the first stage of turbine, which is state 1, is 3.3 into 10 to the power 5 kg per hour. Okay. So, this problem emphasizes the role of an open feed water in improving the thermal efficiency of a Rankine cycle, which involves regenerative concept. With this, I conclude. Thank you for your attention.